Okay, in the previous study, we learned how the phase margin will affect stability of the negative feedback system. Actually, for any negative feedback system, we usually need to tune its phase margin to achieve the optimal control. So in this section, we are going to study how to design the fundamental compensator network for the closed-loop control. So first, let's look at the typical specs for a closed-loop control system. So usually for a closed-loop control, we need to achieve multiple targets. The first target is we want to have the output resist the load current variation. So we can write the mathematical expression for the output voltage to the load current transfer function. Vs over load current is I load. Given the condition that the other small signal disturbance are 0, line inputs small signal equals to 0, and also the reference is unchanged. So this will be equal to the output impedance divided by 1 plus loop gain. Okay, so the second target is we want to have the closed loop system to resist the input voltage variation. So this means that even if the input voltage changes, we still want to maintain a stable output voltage if we consider the output voltage is the output signal. So similarly, we can also write an expression for the transfer function of output voltage over input voltage. Small signal. So for the closed loop system, as we previously derived, this should be equals to transfer function GVG divided by 1 plus TS. So where the TS here are the loop gain of the closed loop system. So in order to resist the load current variation and input voltage variation, so we should have a sufficiently large loop gain T. So if T is large in magnitude, then we can see that the disturbance introduced by load and also by input voltage will be well decayed by 1 over 1 plus T, right? So for such a system, usually we require T to be sufficiently large in magnitude so that we can resist the external variations to ensure a stable output voltage. Next, let's look at the third target we want to achieve. So we usually want to achieve a good, fast, transient response time. So this parameter usually is highly dependent on the crossover frequency. So large, fast transient response time correspond to high crossover frequency in the feedback loop. And the fourth targets or spec is the overshoot or raining in the time domain waveform. A properly designed system should have low overshoot and low raining to ensure a good time domain response, right? So for the control perspective, we usually require an adequate phase margin to achieve light, low overshoot, and raining. Okay, then here comes a design question. How can we realize those targets? How can we achieve fast transient response and light overshoot and raining by properly design the system? So the answer is we can properly design the compensator. So the approach or the solution is that we can add compensator, which usually we express by GCS for its transfer function in S domain, right? So by adding this GCS, we can modify the loop gain TS, because GCS is part of the TS. So we can properly tune those parameters to ensure that those targets are well achieved simultaneously. Okay, next, let's look at what kind of compensators do we have in our practical design. So the first, the very classic compensator, we call it as lead compensator. Or usually we refer this as PD compensator. So the abbreviation P and D refer to the proportional and the derivative, right? So in the mathematical perspective, the PD compensator is just a transfer function of GCS equals to DC bias GC0 times 1 plus S over omega Z and divided by 1 plus S over omega P. So you will see that this is a zero performance and this is a pole performance. So for the PD compensator, we usually want to put this 0 to be in the low frequency range. So this is a low frequency 0. And this pole will be placed in the high frequency domain. So this will be usually a high frequency pole, meaning that usually omega P is much larger than omega 0, right? So this is the essence of the PD compensator in transfer function perspective. And based on this transfer function, we can plot its body plot. So top one is the magnitude plot. Here is the frequency, and the y-axis is the magnitude in dB, right? In dB. So as we previously studied the principle of plotting the body plot, we can see that for a low frequency 0, prior to this low frequency 0, suppose here is the Fz, here is Fp. Before this point should be flat, right? Flat. The level here is GC0 in dB. And beyond this F0, there should be a slope of 20 dB per decade. And when it hit the pole frequency here, there will be a negative minor 20 dB per decade. So the magnitude plot will become flat again. And in the middle here, right, is the like average in log scale, right? Log scale. So the frequency here is the square root Fz, Fp. Okay. Next, let's plot the phase plot. So the 0 will incur a 90-degree phase change, right? And the pole will incur a minus 90-degree phase change. So the change will start from 1/10 of the 0 frequency. So we would have such a profile of the phase plot. So ideally, it's like so here is the 10 times Fp. And practically, there cannot be such an ideal sudden change, right? So we would have a gradually change. So this height here really depends on the distance between those frequencies. If they are really far apart, then the net change here will be plus 90 degree. However, if they are not that far away, then this will be slightly lower than 90 degree. Really depends on the distance between Fp and F0. But there is one thing we are pretty sure is that in the middle point in log scale, we would expect the max phase change over this frequency scale, right? So we mark this as F phi max. So this will be equal to square root Fz times Fp. And at this phi max, we can calculate the phase change for this transfer function, right? So this phase change is denoted as GC phase angle at phi max. So we would calculate that this has its expression as arc tangent square root Fp over Fz minus square root Fz over Fp. So that's the expression for this phase angle change, okay? And also we can calculate the height in the magnitude plot, right? If we substitute the frequency of F phi max into the magnitude plot, we can calculate the level here. We will see that the level here will be equal to GC0 times square root Fp over Fz. So that's the entire phase phase plot and the magnitude plot. And based on this expression, we can also, if we denote that this phase angle equals to theta, where theta is the maximum phase increase contributed by the PD compensator, right? If we denote this by theta, then we can find out there is based on this formula, we can reorganize this formula. We can find that Fp over Fz will be equal to 1 plus sine theta divided by 1 minus sine theta. So this tells us that theta really depends on the ratio between the pole position and the zero position. Okay, so actually we can plot the curve of maximum phase lead versus the frequency ratio. So we would see such waveform. So for this plot, the x-axis is the ratio of the pole and the zero frequency for PD compensator. And the y-axis is the maximum phase lead. We will see that, so suppose that this is in log scale, here is 10 times, here is the 100 times, here is 1,000 times. And in y scale, here is 0 degree, here is 45 degree, here is 90 degree. We will see that with the increase of the frequency ratio, the theta will rise correspondingly. So we will see such a behavior. If the ratio is sufficiently large, like 1,000 times, they are really far away, we can think that they are not cross-coupled, right? So the zero will eventually contribute a 90-degree phase change. But if they are really close, right, really close, then their phase contribution are canceled. So there is 0 degree maximum phase lead. So by checking this waveform, we can properly design the pole and zero frequency to achieve the phase lead we want to contribute by introducing the PD compensator. All right. Okay, now let's erase the blackboard. All right, we have erased the blackboard. Now let's try to introduce an example to show you how we can utilize the PD compensator. Suppose that we have a uncompensated system for the closed loop control. So we have its body plot behavior like this. So this is the frequency. This is the magnitude of the loop gain in decibel. And the original uncompensated body plot like this. So initially it's flat. And here at this F0 frequency, we have a quadratic pole response. So there is a bump. And then after this quadratic pole, it decreases at minus 40 dB per decade, right? So for example, here is the 40 dB, 20 dB. So this is a very typical body plot behavior in the power converter, right? For the closed loop gain T. And here we denote as the gain crossover frequency as Fc. Correspondingly, we can plot the phase plot. So here is the phase angle for the loop gain, T. 0 degree, minus 90 degree, minus 180 degree. We know that the quadratic pole will eventually contribute a minus 180 degree phase change, right? So if the quality factor is high, we would have a fast change of the phase. So the phase plot will be usually like this. So here is F0, quadratic pole. Initially, phase change is 0 degree, right? And there is a sudden change of minus 180 degree. So from this body plot, we can see that at the crossover frequency, right, the phase change is almost minus 180 degree. This means that the phase margin is really, really small. Although the system is stable, however, the phase margin is too small, which would incur poor dynamic performance, right? So we need to compensate this loop gain, right? So the target, how to compensate, right? Target is that we want to reach phase lead theta at the gain crossover frequency. Right? So if we can introduce a phase lead, we can for sure increase the phase margin to a proper value, right? So the dynamic response will be improved. So based on this target, we can use PD compensator as we previously analyzed, right? So this is the maximum phase lead. We just need to properly design the PD compensator to ensure that at this FC frequency, we would have a theta, right? Theta phase lead to the system. That will be fine, right? So basically, the principle is that the PD compensator should have is the pole and 0 frequencies should be selected, right? Should be selected as based on the mathematical relationships, right? So Fz equals to crossover frequency Fc, right? Times 1 minus sine theta divided by 1 plus sine theta. Correspondingly, Fp, the pole frequency, can also be properly designed by the principle here. So Fp should be designed as Fc times 1 plus sine theta over 1 minus sine theta. So now the omega z and the omega p can be determined, right? The last parameter to be determined will be the decibels, GC0, right? For decibels, there is a relationship, right? Because we don't want to change the crossover frequency point. So at this frequency, the magnitude of the PD compensator should be equal to 1, right? Therefore, the crossover frequency is unchanged. So at Fc, the magnitude of the compensator should be equals to unity, right? Then by referring to this formula, we can solve the GC0 should be equal to square root of Fc over Fp. Okay, So now, coming back to the body plot, right? We can see that what is the compensated system performance. So first, there is DC bias, right? Because the pole frequency is higher than zero frequency. So this is a negative value in decibel. So the compensated, I will use the red chalk to plot, right? So here will be a phase, the magnitude drop, right? Drop, because this value is a negative value in decibel. Then we would have a quadratic pole response. And we have introduce a zero, right? And pole. So here is the zero frequency, Fz. So zero frequency will incur a change of the slope to be up by plus 20 dB per decade. But this is still unchanged, right? So the crossover frequency is unchanged. So it still hit the zero at this Fc point. And then we would have a pole. So here is the pole frequency. So beyond this pole frequency, there will be minus 20 dB per decade, right? So this is minus 40 dB per decade again. And regarding the phase plot, so the low frequency phase is unchanged, right? Unchanged. But beyond this quadratic pole, right, we just check this one, right? Basically, this compensated phase change will be the compensator plus the original, right? So we would have such a performance. So here, like we add this bump to this original phase plot, right? To this original phase plot. So here we can achieve a phi m. Phi m is the tuned phase margin, right? Tuned phase margin is really determined by our designed value, theta. So we can see that we can achieve a improved phase margin, all right? So we can see that in this section, we can see that the PD compensator can be utilized to improve the phase margin performance. Basically, we can precisely control the phase lead we want to introduce to this loop gain. So by improving the phase margin, the dynamic response can also be improved.